Okay, so matrix notation, what for? In the last section, we learned about linear programming problem, okay? Linear programming problem, which is about minimization and maximization of the objective function under some constraints on the variables, okay? If the constraints are all of them equality less than or equal, as we see here, then we will say that linear programming is in a standard form. So we have seen the linear programming problem in general, where constraints on the variables may have less than or equal, some of them greater than or equal, some of them equal. So these are the inequalities or the equalities. But if the constraint contains only less than or equal, then the linear programming problem is called the standard form, is called to be in standard form. And if the constraints on the variable are all equalities, not inequalities, equalities, which means equal, then the linear programming problem is said to be in canonical form, and we will use that. Okay, now let's go. What we will start today with is rewriting the linear programming problem as matrix notation. That's it. So it is a matter of notation. So we will have fun today. So consider the linear programming problem, which asks us to maximize the function z under all of these constraints. And actually, this is given in standard form, as you notice. Why it is in standard form again? Because all of them are inequalities, less than or equal. Okay, now if we write this matrix, if we take the coefficients in here, in the constraints, the coefficients from the inequalities in the constraints, and make a matrix out of them. Okay, now we are looking for what values of x, the vector, which means x1, x2, x3. So we will take these variables and put them in one vector. Okay, we already know that. And we will take the constant in here in the constraints and make a vector out of them. And then we go to the constant c1, c2, cn in the objective function and make that vector out of it. Using all of that, then the whole linear programming problem is transformed to matrix notation. So z, this z here, will become C transpose times X. You notice this is C transpose is C1, C2 all the way to Cn. Now when we say times X, this is a matrix multiplication. X1, X2, Xn. So if I say times X, then this is what I get: C1 times x1 plus C2 times x2 and Cn times xn. And then we get back the function. Okay, and I think you can easily see how we got this for the constraints, actually. And don't forget the variables must be non-negative, positive or zero. Okay? Okay, so this is the matrix notation. Good, that's all. We need to say more about that. Let us start with the following definition. A vector x from R or n satisfying the constraints of the linear programming problem is called a visible solution to the problem. Okay? Visible solution to the problem. If we go back to the linear programming problem, it asks us to maximize, okay? So we are looking for the optimal solution for the values of x1, x2 to xn that maximizes z. But there are others. Okay, let me say that statement again because I want to involve the constraints in that. Okay, maximize here means finding the values of the x1, x2 to xn that satisfy the constraints. So that satisfy all these constraints and maximizes z. And these variables, these values of this variable must be non-negative. Okay? And then the values that maximizes z under these constraints are called optimal solution. Now, there are other solutions, other values of the x's that satisfy the constraints, but they don't give a maximum solution, maximum value for z. They are still called solutions, but not optimal. So the value is the vector of x that satisfy the constraints is called visible solution. Okay, here we go. Visible solution if it satisfies the constraints. Okay, we have the definition in there. Okay, visible solution. And below there is the one I said about, the optimal solution. The visible solution that maximizes or minimizes the objective function is called optimal solution. So the goal of the linear programming problem, to solve it, we need to obtain the optimal solution. Other vectors that satisfy the constraints are called visible solution. Okay, the optimal solution is a visible solution because it does indeed satisfy the constraint. Okay, good. Let's keep going. Okay, so let us apply what we have made of notations to this example. Remember, this example concerned the lumber mill. Produces two kinds of boards, the finished grade board and the construction grade board. Okay, and it uses two machines or two processes. First process is rough saw. Okay, second process is planing. So first process was المنشار الخشن. Okay, بياخذ الخشب بودوه على المنشار الخشن، بعدين المنشار الخشن بودوه على التلميس. Okay, so تذكروا هذا المثال because we will do some referring to there in life. Okay, and I will mention that again. So the model, the linear programming problem of that example was to maximize the profit under these conditions, constraints. Remember, this number 8 is the number of hours that the rough sawing machine operates, and 15 the number of hours that the planning machine operates. Okay, so okay, moving this to matrix notation. So z is this vector times that, and good. So 2 2 in here, 5 3. Take them and put them in rows. Here we go, and we are done. Good. Now notice that x1 is a visible solution, x2 visible solution, x3 is visible solution. All of them are visible. Why? Let's say here why they are visible solutions. Because they satisfy the constraint. Like if you substitute x1 here in this place, and then it will satisfy the equation. So let's do it. So I will go and say, okay, I want to see 2 2 5 3 times x1, which is 1 2. So let us do the multiplication. This is 2. Let us do the multiplication. Now if we multiply, we get 2 plus 2, which is 6 in here. And then we get 5 plus 6, which is 11. Oh, good. This is indeed less than 8, 15. Now I forgot to mention something. What do we mean by a vector to be greater than 0, or a vector less than or equal another vector? It means we will compare the components. This component is less than this, and this one in here must be less than that. Okay, and this one in here less than this. So let me write that in general. I mean by, for example, d1, d2, all the way to dn to be less than or equal b1, b2, all the way to bn. That means di is less than bi for every I. Okay. Okay. Now, so x1 is a visible solution. What's about x2? Shall we try that? Okay, let's go for it. 2, 2, 5, 3, multiply it by x2, which is 2, 1. Do the multiplication. We get 4 plus 2, which is 6. This is not negative, okay. And 10 plus 3, which is 13. And this is indeed less than or equal 8 and 15. So, and easily you can check it for x3. So they are visible solutions. Why? Because they satisfy the constraints. Is any one of them an optimal solution? We don't know. We don't know. Okay. Let's go again to vector x4 and x5. It says they are not visible solution. Oh, why they are not visible solution? Let us see. Let's go take x4 in here and multiply it by the matrix and see what we get. 2, 2, 5, 3 times 3, 1. Okay, let's do the multiplication. 6 plus 2, this is 8. And 15 plus 3, which is 18. Oh, this is not less than this vector here. It is not. So this is not visible solution. Same thing for x5, not a visible solution because each one of them does not satisfy the constraints. What about x6? It says here it is not a visible solution. But if we multiply the matrix with this vector, let's multiply it. Negative 2 and 3. Then what we get? We get 2 and we get 9, right? Oh, this thing is less than the vector there. So what is the problem? Somebody tell me, please. This is less than 8 and 15. But still, this is not a visible vector. Somebody tell me why it is not a visible vector. Somebody say.
Because it's less than 0.
Okay, good, thank you. Because one of its coefficients is negative. It did not satisfy this thing here. This is why it is not visible. Good, thank you. Okay. Okay, so we said we don't know yet whether any of these optimal solutions is, any of these visible solution is an optimal one. We don't know. They are just visible solution. How can we obtain the optimal solution? We will learn that next section, okay? But here we are telling you, the book is telling us that this vector here is the optimal solution. It says 3 over 2, 5 over 2. Do you remember what these values mean in our example of the lumber mill? X was referring to what? Number of tons of the finished grade brand, finished grade board. Number of feet, 1000 feet. Number of finished grade board, 1000 feet board. This is for the first component, 3 over 2. This is for x. And y, this is for x, and this was for y. And this was the number of the construction grade 1000 feet boards. Okay, now why are we mentioning these things to remember? Let me show you why. Okay, good. So we learned that we have a linear programming problem in standard form and linear programming problem in canonical form. The canonical form, the constraints in there are all equalities, equal, okay? But in the standard form, they are less than or equal, they are inequalities. Now the idea here, we want to convert the standard form to a canonical form, okay? Why we want to do that? Because in the canonical form, we have equalities. So, according to what we have already learned, converting linear programming problem to a linear to matrix notation, then having a canonical form, the matrix notation of it will be a linear system. And you know how to solve linear system using Gauss-Jordan and using any method. Okay, so this is what I'm saying here. We want to change the inequalities to equalities, okay? We are talking about the constraint. Doing so, we will be converting the standard linear programming problem, converting it to a problem in canonical form, okay? Now, canonical form is a system of linear equation, and we can use methods of linear algebra you have learned, such as Gauss-Jordan reduction, to solve it. And good, when we solve it, we get the solution, and then we bring the solution back to the standard form. How we do this? Now the question, how the solutions of the standard form is related to the solution of the canonical form and vice versa. If I have a solution in the canonical form, how I get out of it a solution to the standard form. Okay, this is what we will see now. Okay, now in the standard form, you know that the constraints are given this way. Agree? They are given this way using less than or equal. Good. Now what we will do, the one to your left, the one to your left now, to our left, is less than the expression to our left, the linear expression to our left, is less than the constant bi in the right. So we need to add something positive to the left so that we make them equal, right? And that's something we add, we will call it slack variable. Slack variable. Slack means thiqal. We put some more weight to the left side to make it equal to the right side. And that slight variable, we will call it, we may call it any name, u, v, anything. But to make things a uniform, to make notation gets together smoothly, we will call that variable x n plus I. Why we call it n plus I? Because this constraint, I here in this constraint, if you notice, change the I to 1 gives you the first constraint. Go back here and see it, down here, gives you the first constraint. Change I to 2 gives you the second constraint, and so on, you know that. So having this happening for all I from 1 to m, so we have a m of constraints. Okay. So we will add xn plus I. Okay. So for instance, look in here what we are doing. This will be explained. Okay. So this is what we add. We add something to here plus something to make it equality, to make this equality. So we add it here. And we must stipulate that this new variable is non-negative, so that it does not go against the constraints itself. Okay. Now look how we do it. Okay. So in here we will add, see, it is added here now. This constraint, the first constraint, is moved to be that. Okay? The function is still the same. The function, the objective function we want to maximize is still the same. Now we are here in standard form and we are converting it to canonical form. Okay, now if you look at the second constraint, we added xn plus 2. That's because I is 2. And we keep doing so. The last constraint, the mth one, we added xn plus m. And here we go. All of these new variables are positive and the original ones are positive. Okay, what is the idea here? What it says here, look. Now the system to the right, here, this system above me, can be solved using linear algebra, right? You can solve it. So we go and solve it and then we obtain a solution. So suppose y hat is a visible solution for the canonical form with equalities. From this, after we get this, we can obtain a solution from it. A visible solution for the original linear programming problem in standard form. Okay? How we do it? Just we truncate the coordinates corresponding to the new variables that we added, which means we take y1, y2, y3 all the way till we reach yn somewhere here, and then we take them, and here we go. This is the solution, and we truncate. So the ones we left behind, what are they? They are yn plus 1, yn plus 2, all the way to yn plus m. So we truncated these things. Good. So convert standard form to canonical form. Make a solution for a canonical form using linear algebra. You get a solution. Truncate the new coordinates we added, and then you get a solution for the standard form. Okay. Okay. Good. Now one may ask, what if I have a solution for the standard form? Can I obtain a solution for the canonical form? Yes, actually. How we, like, I'm asking here if we have that and then we want to obtain this, how we do it. For example, how we do it, how we get, here we have y1, y2, yn. For example, how I get yn plus I, how do I get it? Simply go here, go back here. Now, you see this variable here? This yn plus I is taking the place of this, because we are saying that y is a solution, the vector y is a solution, n plus I, okay? And this goes for yn, this y2 and y1 is plugged here. Now, using this equation, you can decide what is y n plus I. It is bi minus ai1 x1 minus all the way ain xn. Good. So this way you will obtain. So here we go. I would like to write this here again. Minus ai1 x1. This is 1 minus all the way minus a I n x n. So okay, so let me summarize what I said. If we have a solution y1 y2 to yn for the standard form, okay, use these coordinates y1 y2 yn to produce yn plus 1 yn plus 2 all the way to yn plus n m, then you get the vector of the canonical form. Now conversely, if you have the vector of the canonical form, the solution in there, truncate the new ones, and then you get back a solution for the standard form. So solution here gives a solution here and vice versa. They are corresponding. Good? Okay. So now this is the idea. I start with the standard form, convert it to canonical form, solve it in there, and go back to give the solution for the standard form. Thank you very much. This is what you want to see. Now this is an example. Let's go back to our example of the lumber mill. Okay, so we wanted to maximize this under this constraint. Now we want to make this equality, so we introduced u. This was for y n here is 2 because we have two variable yn which is 2 plus 1. Okay, 2 plus 1, and this goes for this goes for not a solution yet. This is x. I mean, okay, what I'm saying in here, if x1 is x and x2 is y, so I want this to match with the notations we have already seen. Okay, now what is x3? Now x3, what is x3? It is this. This is what we are adding. How this came out to be, because n is 2, this is n plus 1. And now this is what? This is x4. Why? Because it is x2 plus 2. Now here n is 2, right? Because we have two variables. Now this goes for I. This is I equals 1. So this is I. And this goes for I. Again, this is I. So good. So we introduced x3, but the book here used u and v instead of x4, x3 and x4, because it was using already x and y instead of x1, x2. Okay, anyway. Now, this is a visible solution, right? Remember, did we check that out? This is a visible solution as a vector. This was a visible solution. Okay, now compute u and v out of these two coordinates. Yeah, okay, so which means x takes 1, x takes 2, sorry, this is x, this is y. So go for 2 here for x and go for 1 for y, and then that will gives you what u equals. It equals 2. There we go. We are just computing. And again, go 2 for x in here and 1 for y, and compute for v, and v will gives you 2. So great. If we add now u and v to x and y, we get a visible solution of the canonical form. Okay. Remember, this is the canonical form and this is the standard. So a solution of standard form has been converted to solution of visible form. Now let's do the opposite. Let us take a solution, a visible solution of the canonical form. So this is a visible solution of the canonical form. X equals 1, y equals 1, u4 and v4. Is it really a visible solution for the canonical form? Check it out as we have already seen. Make sure it is indeed a visible solution. Okay, each one of them is let me do that. Each one of them is positive. Now, what is the remaining is to make sure now do the matrix. 2, 2, 1, 0, 5, 3, 0, 1. This shall be multiplied by this vector here we get from here, which is 1, 1, 4, 7. Where did I get this matrix from? Where did I get this matrix from? It is from here. Okay, so we need to multiply these things together, and it must be less than or equal 8 in here and 15 in here. Not less than or equal. The whole idea, we missed the whole idea here. It is equal, right? Good? Okay. Good, so this is a visible solution. So just take the first two, gives you visible solution of the canonical form. Take the first two, gives you visible solution of the standard form. Let's move down there. Okay, now, what does these numbers means for the example of the lumber mill? Remember, okay, let me go down here. Let me go down more, and I want to erase everything. Let me clean all that. Clean. Good, very clean now. Look what is happening. Do you remember what that means? 2x plus 2y less than 8. That was 8 hours of the rough saw منشار الخشم, because the rough saw worked 8 hours at most, and this was for 15 hours for the planing التلميس. Okay, so 2x plus 2y بيعطيك الوقت, gives you the how much you work on doing the rough saw, and 5x plus 3y gives you how much you work in the machine of planing. Okay, therefore you here means الوقت اللي انت ما استعملته في هذا الماشين. So you here means the difference between the time you can use the machine, which is 8 hours, and the amount you used the machine. الفرق بيناتهم. انت بتقدر تستعملها 8 ساعات، لكن ممكن انت افضل حل لك ما تستعملها 8 ساعات، تستعملها 7 ونص. ليش؟ لانه بدك وقت الاخر يروح للآلة الاخرى مشان تعطي ربح اكثر. ممكن. And also V is the difference between 15, the availability of the plane machine, and how much you worked on it. And this is what it says here. Okay, so this paragraph tells you that. And now look what's happening. The optimal solution will tells you how much to work, how much time to use the first machine and how much time to use the second machine. And now, surprisingly, the optimal solution, which we will learn how to get, we don't know how to get yet. Okay, tells you that U is 0 and V is 0, which means you will use both machines all the time. Good. And this is a visible solution indeed for the canonical form. Okay, good. Now, oops. Okay, please give me a break. Yeah, come on. Okay. Good. So at the end we will see, just convert. I did it already in this example. I cleaned. I made a matrix for the new canonical form after adding the new variables. I did it for that example, but here we do it in general. Okay, so this is the canonical form, adding this new variable, a new variable, a new variable. And we know when you now take the matrix, it is the very same part in here as the standard form, but the identity matrix part looks an identity in here, right? Identity matrix. Yes. Okay. Okay, good. Now this is the matrix of the canonical form. Yes, this part should be square, so it looks identity. And this vector b, we know it. Now this is the same as our previous vector if we truncate it from here, but adding this new to it. And the c, we will add to the c these ones, the zeros, and this the old c of the standard form. So in here is let me do them better. This is the part of the standard form, adding those, and this is the part of the standard form, and adding these new ones. Okay, these new ones. Okay. Okay, and okay, this is the matrix I have already done. So if we have our original problem, and we added this, we added that, so the matrix become this 2 2, and we have 0 here, and 5 3, and we have 0 here. So 2 2 1, and this was 1, and here 1 2 2 1 0, and okay, and I believe everything is clear, and thank you very much. We are done with the lecture.